Hi, my name is Jalalu, and now I'll be talking to you guys about my final year project, OFDMA implementation on a software-defined radio in the Monash University. So, what is software-defined radio? Software-defined radio is a radio communication system where components that have been traditionally implemented in hardware are instead implemented by means of software on a personal computer or embedded system. So, how do we build a software-defined radio? This project manages to study the transmission part and reception part for the software-defined radio. The transmission and reception part are mainly based on the orthogonal frequency division multiple access digital modulation method, which we call OFDMA. OFDMA is a multi-user version of the popular orthogonal frequency division multiplexing, which is the OFDM. Now, let's look at the difference between OFDM and OFDMA. The main difference between an OFDM and an OFDMA system is in the OFDM, the user are allocated on the time domain only, while using an OFDMA system, the user would be allocated by both time and frequency. OFDMA is better than OFDM as, for example, user 1 might have a better radio link quality on some specific bandwidth area of the available bandwidth. Now, this video will be showing the final outcomes of the project. The first will be the modulation result. The left one will be the QPSK modulation, which has 4 constellation points on the plot. The middle one is the 16 QAM modulation with 16 constellation points on the map, and the right one is the 64 QAM modulation, which has 64 constellation points on the map. We will discuss about the result later in the video. The next one will be the baseband power spectrum. As you can see, user 1 is allocated in the frequency range from negative 250,000 Hz to 0 Hz in the baseband, and user 2 is allocated from 0 Hz to 250,000 Hz. This indicates that the users are allocated in different frequency domain, which has implied the OFDMA modulation. This project also manages to study the relationship between the distance of antennas and the stability of the signal. As we can see, if the antennas are touching each other, the signal will be very unstable, and the stability is increasing when we increase the distance between the antenna at the transmitter side and the receiver side. Now, let us have a look at the transmitter part of the OFDM system. The data will first be transformed to parallel bits and then mapped on the constellation map as constellation points. Then, the data will go through the IFFT block in order to transform the data from frequency domain to time domain. Before the cyclic prefix is added to the data will be transformed back into serial form. Once the signal is added by the cyclic prefix, it will be converted to analog form and filtered by the low-pass filter. Before the data is transmitted, the additive white Gaussian noise will be added to the signal also. At the receiver side, the cyclic prefix in the data will be removed and then be transformed to parallel form before going through FFT block in order to convert the data from time domain to frequency domain. These are the basic types of modulation where the video has shown most of the result at the beginning. In the BPSK modulation, the signal will be mapped into constellation point and each point represents a signal having a difference of 180 degrees. It doesn't particularly matter exactly where the constellation points are positioned. In the QPSK modulation, the signal will be mapped into the constellation point, and each point represents a signal having a difference of 90 degrees. In the 16-quant modulation, all the constellation points which are mapped on the map are the combination of 4 bits. Each combination of 4 bits represents a signal with a different degree and an amplitude on the constellation map. Multipath effect is a main factor which will affect the signal. As you can see, when the signal is transmitted, it will not be received by the receiver straight away, but got reflected by the building, then only received by the receiver and cause some delay. There are some solutions for this multipath effect, which are build the transmitter and receiver at a very high point, which the signal will not get reflected anymore, or by adding cyclic prefix to the signal. It is easy to see that the second solution is more practical. The reason we are adding the cyclic prefix is to avoid the inter-symbol interference and the inter-carrier interference in the signal. In ISI, if the cyclic prefix is not added and the signal sent will have some delay, this would cause some data overlapping at the receiver side. After adding the cyclic prefix, the guard interval will be served as a protection for each of the OFDM symbol, and as long as the length of the cyclic prefix is longer than the impulse response of the channel, there is no ISI in the signal. The ICI is mainly caused by 2 factors, and they are when the delay spread of radio channel exceeds guard interval and there are frequency offset at the receiver. Now, we will be discussing about how the location of antenna affect the signal. If the antennas are set too close, signal could get reflected by the hardware and produce ISI in the signal. If the antenna are set too far from each other, there will be more delay in the signal, since this transmission and reception are exposed in a bigger multipath environment. This is the hardware that this project uses for the simulation, which is called NIUSRP. Those probes on the hardware are the antennas of our system. The software that is used here for constructing the transmitter and receiver is LabVIEW, and the connection cable between the PC and the NIUSRP is PCIe X4. Now, the video will be showing the simulation part. Before we start our simulation, we should check that if the probes are connected tight enough to the port of the hardware. We can check the transmitter and the receiver are working or not by observing the light on the device below the probes. Those red lights represent the transmitters, and the green light with the label RX2 is the receiver. Our first simulation is to test the modulation result when the probes are touching each other. Always remember to run the receiver first, as the receiver has to be ready before the transmitter transmits the data. As you can see, the constellation points are not located at the desired location, as the signal sent from the transmitter has been got reflected by hardware to hardware, and then only received by the receiver, which has caused delay. The next one will be a distance of 4 cm between the probes. Repeat the same steps as before. We can see that the constellation points are not that stable, as they sometimes located at the desired location but sometimes didn't. Now, we will set the distance be more than 8 cm between the probes. This time, we can observe that the constellation points are always stable throughout the simulation. Now, we will be simulating our design with hand as obstacle, placing between the transmitter and the receiver. Repeat the steps as above. We can see that the signal is not stable as the obstacles has interfered the transmitted signal. In conclusion, this project manages to study that the distance between the antennas is important in order to transmit and receive the signal perfectly. We can also observe that OFDMA is better than OFDM because OFDMA is not only allocate the user in the time domain but also in the frequency domain. This comes to the end of the video. Thank you for watching.